Welcome, my name is Dr. DrWedding, and this is DrWedding, DC10. Kirchhoff's voltage law. In this video you will learn what Kirchhoff's voltage law is, and how to use it. KVL is covered early in this series because it is easy to understand when it is demonstrated on a very simple circuit. This video is only designed to teach you what Kirchhoff's voltage law is, along with some basic uses. More advanced applications will be covered in later videos. If you are trying to learn mesh analysis to solve series, parallel circuits with multiple supplies, then this is not the correct video. Mesh analysis is covered in detail in a later video. Even if your goal is to learn mesh analysis, you should watch this quick video. Without a firm understanding of KVL, you will not understand mesh analysis, and you will not be able to correctly create the equations used to solve the circuit. Kirchhoff's voltage law is shown below. KVL states, the sum of the voltages around a closed loop is zero. Looking at this equation may be intimidating, but it is extremely easy to understand and use. The KVL equation starts out with the Greek letter sigma. In mathematics, sigma means to add up a list of numbers to get the sum. The list you are adding up is a list of voltages. To keep the voltages organized, we will give each one a subscript. The letter I is a variable that will start at 1. Because each circuit is unique, you do not know how many voltages will be in the list. In mathematics, the letter N is used to represent the end of a list. And as long as you start and stop in the same position on the circuit, the voltages will add up to 0. Sometimes the equation is written in other ways, as shown below. If you see KVL written either of these ways, it is the same as the previous equation. When you first encounter Kirchhoff's voltage law, you may be thinking, how can the answer be 0 if you are adding up a list of values that are not 0? Think of a circuit like this wavy slide that you might see at a county fair or on a playground. We have been using height as an analogy for voltage. And the slide has a ladder that you can use to go up into the air. This is just like the voltage supply. As you slide down the slide, there are sections that take you down. The sections that reduce your height are like the resistors in the circuit. The voltage in a circuit is made up of both positive and negative values. So Kirchhoff's voltage law is really saying, if you start at a random spot in the circuit, move around, and come back to the starting point, your net change in height is 0. If you start at the bottom of the ladder, climb up to the top, slide down the slide, and go back to the bottom of the ladder, then your net change in height is 0. If your net change was not 0, you would be floating above the ground, or your legs would be sunk into the ground, just like a glitchy video game. It does not matter where you start. As long as you return to the starting point, all of the positive values and all of the negative values will cancel out, and your change in height will be 0. So if I am 6 feet off the ground at the top of the slide, then I slide down to the ground, and then climb up to the top of the ladder, then I end up 6 feet off the ground. Because I start 6 feet off the ground, and I end 6 feet off the ground, my net change in height is 0. The path I take does not matter either, just as long as I close the loop by ending at the starting point. For example, when I am at the bottom, I go back to the top of the slide, where I stop, and I turn, and I go for a ride, till I get to the bottom, and you will see that again. My change in height is 0. In example 1, KVL will be demonstrated using the circuit on the left. We have solved this circuit in 2 previous examples, so we know the voltages. Pick any spot on the circuit. It does not matter. In this example, we will start just under the power supply on the lower left of the schematic. This is like standing at the bottom of the ladder on the slide. Now we need to pick a path. In this example, we will go clockwise around the circuit. As we move around the schematic, the voltages we encounter must be recorded. The first voltage that we cross over is the 12-volt supply. When moving clockwise, we hit the minus sign first. So this is recorded as minus 12 volts. This is equivalent to climbing the ladder on the slide. Then we move across the top of the schematic where we encounter the 4.5 volts across R1. When moving in this direction, we hit the plus sign first. So this is recorded as plus 4.5 volts. This is equivalent to sliding down the first bump in the slide. Then we move down the right side and across the bottom of the schematic, and we encounter 7.5 volts across R2. When moving in this direction, we hit the plus sign first. So this is recorded as plus 7.5 volts. This is equivalent to sliding down the second bump and returning to the bottom of the slide. When all these voltages are added together, the total voltage is 0 volts. In example 2, we will start between the two resistors and go counterclockwise. This is similar to starting in the middle of the slide. As we move across the top of the schematic from right to left, we encounter 4.5 volts across R1. Because we entered on the side with the minus sign, the voltage is recorded as negative 4.5 volts. If we then turn around, we will encounter the same 4.5 volts. This time we hit the plus sign first. So this is recorded as plus 4.5 volts. This is like turning around at the top of the slide and coming back down. We are back to where we started from. So if we add up these voltages, we will get a net change of 0. You can see on the slide that if you start and stop at the same point, the net change in height is 0. There are many good uses for KVL. The first is checking your work. In a series circuit, the supply voltage is what takes you up the slide, and the resistors take you down the slide. So, in a series circuit, the sum of the voltages across the resistors will equal the supply voltage. In this example, the voltages across the three resistors are 4 volts, 8 volts, and 13 volts. The sum of these three voltages is the same as the 25-volt supply voltage. If these two values did not match, that would indicate that you made a mistake. The next two reasons to learn KVL involve information we have not covered yet. But I will briefly mention them so you understand that KVL is very useful. The second use for KVL is to help you find missing values in a series, parallel circuit, as well as verify each step. This will be demonstrated when this topic is discussed. The third use for KVL is to perform mesh analysis on a series, parallel circuit that has multiple supplies in it. Mesh analysis is covered in a later video, but here is a quick overview. Mesh analysis is when you go around a loop in a series, parallel circuit, and add up all the voltages. You use variables for the unknown values. When you return to the point where you started, you set the equation equal to 0. This is performed with different loops so you can generate multiple equations. The equations are then solved simultaneously to find all the missing values. It sounds scary, but it is very easy. I hope that this video has helped you understand Kirchhoff's voltage law, often called KVL. KVL has many uses. At this point, you can use it to verify the solutions in the circuits you are solving. As you advance through this video series, you will be introduced to more uses for KVL, such as helping you solve series, parallel circuits, and performing mesh analysis. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.